Good morning, dear students, and welcome to Vista's Learning, an online educational platform. My name is Denzil, your science tutor for class 11. So let's get started with our session for today. I have an interesting topic to discuss with you. This topic is based on understanding the two physical quantities such as mass and time. This is a session 2 of the chapter measurement. So in the session 1, we discussed the basics of length. What exactly is this physical quantity length? What are the ways to measure length? The given SI unit of length is meter, and how can meters be identified in a smaller terms and also in a larger terms. Smaller terms like the centimeters, millimeter, micrometer, nanometer, picometer, femtometer. And when it comes to larger, it would be kilometer, light years, parsec, and also the astronomical unit being the distance between Earth and the Sun. So this time, we will be discussing these two physical quantity of mass and time. So let's get started without any further ado as to the measurement of mass. So what exactly is mass? Now that you have understood a little basic of this physical quantity of length, well, mass is one such quantity which is dependent on the property of a matter. So mass is a basic property of matter. Mass is also the measure of inertia. Now, I tend to ask this question to students who are of lower classes of 9th standard, 8th standard, basically the high school students. The question that I phrase to these students is, in order to push a car forward, is very difficult as long as the car engine is turned off and the brakes are off. It is difficult to push the car. Though the gravity is acting downwards, gravity is certainly not acting on a sideways direction, which means it is not opposing to your applied force. There is a resistance force to the motion of that car which is called a friction, but friction will take it to be negligible because the friction that you're dealing here is called a rolling friction. So when you're trying to push the car, you find it very difficult to push the car, almost impossible, though there is no gravitational force which is acting on a sideways direction. So why is it difficult to push that car? Now that is because of inertia. The resistive property of an object which remains in a state of rest or in a state of motion. This resistive property can be measured by using mass. More the mass of the object, more will be the inertia, meaning the resistive property of a body. So what would be the SI unit of mass? The SI unit of mass is kg. And what does kg stand for? Kilograms. Kilograms. So what is a kilo? Kilo itself is a unit which symbolizes 1,000. So 1,000 grams represents 1 kg. So how exactly did this 1 kg come into the picture? It was certainly not God-given. So how was it that we introduced this concept of a kilogram? It all began with this standard weight or standard mass. The weight is completely different from mass. So let me come back to mass once again. A standard mass which was created by using two different metal elements such as platinum and iridium. So platinum, iridium, when combined together, you create a standard mass of 1 kg. And this standard mass of 1 kg, as you see in the picture, that metal is stored right here at the center, and then it is covered by glass so that it is not affected by the outer atmosphere. So this mass is considered to be 1 kg, and all the other mass that you notice as you go to the shop. When you go to the shop and try to purchase 1 kg of apple, what the vendor does is he takes the pan, which is called the balancing beam. On one part he puts apple, on one pan he puts apple, and on the other pan he puts a standard mass of 1 kg. Now, how is that a standard mass of 1 kg? How did that come into existence is due to this particular platinum iridium rod. Those masses have been replicated with other such metals. The metals that are currently used in case of weighing balance is iron. But that iron is a replica of the same exact mass of this particular metal. Now you may ask the question, or I would rather ask the question to you, why exactly do we have to use these two different elements, that is platinum and iridium? Why not use some other element? Why can't you use iron instead of this? Platinum is costly, it is expensive, so why not use iron? Well, the answer is iron has the ability to rust when it is in contact with air. Platinum, on the other hand, is rust resistant. Therefore, since there is no rust, it does not lose its mass even over time. But given enough time, then yes, probably this metal also would decay. So what could be an alternative? There are such researches going on to find a replacement for a mass, how we could measure a mass using a different experiment rather than using one such metal, which is actually located in a museum, Paris. Okay. So this is how you would measure or create a standard kilogram, where a kilogram itself is 1,000th of a gram. So let's make a quick note of here as to the ranges of this mass. What are the various range? The range that we will be discussing, the range with related to the physical quantities, we'll discuss that later, but we shall look at the various range being for a kilogram. I'll change that color, change color to yellow. 1 kilogram, which is equals to 1,000th of a gram, right? So 1 gram as a conversion factor, what can you write? That 1 gram is equivalent to writing 1 by 1,000th of a kg. Now, if you can recollect the first session that we created on measurement, we discussed that there are different ways in order to measure a mass itself. One way is by using, which is a kilogram. The metric unit that we use here is an MKS system. This is what is called as a metric system. The metric system that we utilize for scientific purposes is MKS. M stands for meter, K stands for kilogram, S stands for, you guessed it right, seconds. But apart from using for the scientific purpose, you also have, when you move to a different country, you have different metric systems such as FPS and CGS metric systems. FPS stands for foot, pound, seconds, centimeter, gram, and seconds. But for scientific purpose, we use MKS metric system. Therefore, remember the SI unit is always a kilogram for a mass. Now, when it comes to measurement of mass of molecules which are small size, you cannot use a weighing balance. You cannot put on the weighing pan and then wait for the number to turn up, because a number will not turn up. How would you measure the mass of a molecule? Well, first of all, to identify this mass of a molecule, we use a name which is a unified atomic mass unit, or simply atomic mass unit, given by the small letter u, or sometimes in your textbook it will be mentioned as AMU as an abbreviated form. So atomic mass unit is a measurement or the unit that we provide to the weight of a molecule or the mass of the molecule. So let me first clarify with the two things, which is weight and a mass. Mass, as we discussed, is nothing but the property of a matter. Weight, on the other hand, is a force that is because of the gravitational pull which is down towards the center of the earth. This gravitational pull down towards the center of the earth what creates what is called a force, and this force is what is weight. So this is how you distinguish the two, mass and weight. So using this terminologies, you must be very careful and I must be very careful as well. So atomic mass unit, U or AMU. So how do you identify this atomic mass unit? One unified atomic mass unit, which is 1U, is 1 by 12th of the mass of an atom of a carbon-12 isotope. 1 by 12th the mass of the atom of carbon-12 isotope. This is how you can identify the atomic mass unit. From this you acquire, which you will also learn soon in your chemistry, as what is called as an Avogadro number, which is the number of atoms that are present in 1 mole of a substance. So including the mass of the, whenever we discuss the atomic mass unit, it combines all the masses of your electrons and the nucleons being the protons and the neutron. So this will also include the mass of the electron, which is 1.66 into 10 raised to minus 27, okay, 10 raised to minus 27 kg. That is the mass of an electron. All right. Now that we have discussed for a molecule, what about measurement of a large mass? Large mass meaning the moon, the sun, or any celestial objects. How will you identify the mass of large objects? Well, difficult. We know that mass of the moon has a certain value. We know that the mass of the sun has a certain value. But how do we know that it has a certain value? Now, this is by using what is called the Newton's law of gravitation. In Newton's law of gravitation, you must have encountered this Newton's law of gravitation in lower standards. But if you have forgotten, that's all right. Let me recap it for you as to what exactly is Newton's law of gravitation and what it states. So first of all, for Newton's law of gravitation, the statement is the force of attraction between two masses is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. I'll repeat it one more time with the equation force of that's good. Force of attraction between two masses, let's say Earth and the Moon. The force of attraction between the two masses, which is Earth and the Moon, is directly proportional to the product of their masses, which is mass of Earth, or let me write that by capital letter M, because mass of Earth is massive So capital letter M, suffix E. Mass of the moon, small letter m, small letter m. And force of attraction between these two planets is inversely proportional to the square of the distance between the two. Now, by putting them together, this proportionality, you get, I'll move to that side, where F is directly proportional to mass of Earth times the mass of Moon divided by the square of the distance between them. Now that you have this proportionality, we need to remove that proportionality by introducing a constant. So what constant can be introduced here? This constant which is been implemented is called a gravitational constant given by the capital letter G, and you write the remaining two as such by r square. So G is called a gravitational constant whose value is 8.86 into 10 raised to minus 12. And the unit would be Newton meter per kg square. So this is what you must have learnt in your high school. So it is a quick recap. By using this formula where F equals to G M M by R square, where F, change the color to some other. I think it won't be visible to you. So F, which is equals to G M1 M2 by R square, to show you these are the two different masses. You can identify what will be the mass of the other object by noting down the force of attraction between the two and also the distance between the two masses. So this is how you can identify the mass of any celestial objects by knowing what is the force of attraction between the two objects. Now, what are the various range of masses? The various range of masses, I've made a note here, so it's been put up here. So have a look at it, starting from mass of an electron, which is almost 10 raised to minus 30. So these are only approximated masses, not the accurate value, but just the estimated and approximated masses. Mass of a proton, which is 10 raised to minus 27. So a mass of uranium atom, which is 10 raised to minus 25. Now I'll be going through only those selected ones, and you can have a look at it later as to what are the various masses. So you can pause the video. And then you can have a look at it as to how the various masses range. All right. So I'll only go through the selected ones. For a raindrop, it's about 10 to the power of minus 6. Grape, 10 to the power of minus 3, which is of a millimeter size. Yeah, but this is of a very small value, which is of 10 raised to minus 3. For a human, 10 square, so almost of 100 kg. Boeing 747 aircraft is about 10 raised to 8 kg. Moon has a mass of 10 raised to 23, an estimated mass of 10 raised to 23. Earth 10 raised to 25, Sun 10 raised to 30, Milky Way galaxy that we live in has 10 raised to 41. And the observable universe is 10 raised to 55. So these are the various masses starting from a small scale to a larger scale as to the size of the universe and the mass that is contained within this observable universe. All right, so now we move on to the next, which is measurement of time. Time is a very essential physical quantity. The time that you wake up to the time that you sleep, you look into your watches, and those watches are designed for a specific purpose only, which is to make note of the time. So Let us look into few history of time, the various instruments that were used in history, how they made note of time. One is by using an hourglass. An hourglass, also called a sand clock, which contains a glass shaped, which is like a funnel, like two inverted funnel. In one you have sand that is contained, and you have a small gap which is introduced between these two inverted funnel. And as it laid in this position, what happens is, due to gravity, the sand starts dropping down. As it's dropped down into the other funnel, it takes certain time. Now that time could be an hour, and therefore we call this an hourglass. You also have a minute glass, which works on the same principle of using a sand, where a sand is dropped between the two funnels, having a small point of contact or small gap in between. Now there's also another way you can measure time, which is by using a sundial. Sundial is by, as the motion of the sun, as the sun rises from the east and sets to the west, during the motion of the sun, a particular dial, which is called a sundial, the shadow cast by this dial will tell you what time it is. This particular picture here, which I'm showing to you, is the world's largest sundial, which is actually located in India. It's called Jantar Mantar, located in Jaipur. So if you ever get a chance to visit to Jaipur, make sure you visit this location, which is called Jantar Mantar. It's a world's largest sundial. So this is like a dial which casts a shadow on one side because of the motion of the sun from one side to the other. And that shadow also moves according to the motion of the sun, which tells you the time. Now, for the measurement of time. In modern times, how do we measure time? Well, one way is by looking at your watch, but that is still not accurate enough. We need better accuracy when it comes to measuring time. So how would we do that? We use what is called as an atomic standard of time, meaning we use atoms in order to determine. We use the principle, the atoms here. We use atoms in order to determine the time, the preciseness of time. So what exactly atom that we're discussing here? The atom under discussion is a cesium atom. Okay, cesium atom is one such element. Cesium is an element. So what happens in a cesium atom? In a cesium atom, there's a vibration that occurs within the atom. This vibration occurs due to the electron spins as they move through the two hyperfine levels. But for this, you don't need to know what are hyperfine levels, since we're starting off with just an introduction to time. I don't want to take you to quantum mechanics, which is a completely different realm. Okay, so we just start with the basic. You have transition of these transition between two different levels, and as the transition occurs, there is an oscillation that takes place, or let's say vibration, because oscillation are those where the number of times, the number of cycles as they go back and forth is less number of times it goes back and forth, we call it oscillation. More the number of times it goes back and forth, we call it vibration. So we keep it that way for our definition, for our understand the difference between an oscillation and vibration. So in case of this transition between the two states, this is how many vibrations that occur inside a cesium atom. That's 9,192,631,770. That is a lot of vibration that takes place between these two hyperfine levels for a ground state of cesium 133 atom. 133 meaning in your periodic table you have the atomic number. So the atomic number for cesium 133. All right. So if that many oscillations occur. So why do we need that many oscillations? So that many oscillations determine 1 second. So 1 second can be broken down into so many parts, which is about 9 billion parts. 1 second broken down into 9 billion parts. So you can find 1 by 9 billionth of a second. So that is why we need atomic clocks for preciseness. So don't worry about this definition of preciseness and accuracy. I shall discuss with you in the next session about this preciseness and accuracy. In India, cesium clocks are actually used as a national physical laboratory located in New Delhi. Yes, in India, we have an atomic clock, which is a cesium-based atomic clock. It is used as the National Physical Laboratory, or NPL, located in New Delhi. And the time that we use here in India is what is called an Indian Standard Time, or simply IST. So the other, what is the SI unit of time? First of all, don't worry about this. This is the SI unit of length, how length is determined. So let me go one step back. Now let us discuss what is the SI unit of time. The SI unit of time is seconds. But in your watches, you have minutes, hours, and also days, which can also keep track of days, and also years. So these are some notion of time, how time can be identified using seconds. You can also identify using minutes, hours, days, months, and years. Now, since we have larger quantity of time, can time be divided into smaller quantities? Yes, time can also be divided into smaller quantities, such as milliseconds, and then you have nanoseconds, microseconds, and also femtoseconds, which is a very, very small value for a time. So you have larger quantity of time and also a smaller quantity of time. To determine the smaller quantity of time, you need to develop an instrument a clock which keeps that preciseness of time. Okay, right. So getting back to the unit of length, now that time can be calculated precisely as to how the preciseness of time is so great now, we can also define our length using this quantity. Length now can be expressed in terms of the distance that light travels in 1 second. Distance light travels in 1 second. You may ask the question, doesn't light travel at different velocity? Certainly not. Light travels at the same velocity in the same given medium. If light is traveling from one medium to another medium, then certainly yes, it travels at a different velocity, which will be discussed in 12th standard, which is your second PUC, where you'll be learning how light bends from one medium to another, which is called a refraction, as also light reduces its velocity when traveling from one medium to another, reducing or increasing depending on the medium. So it has been expressed in terms of a path that light takes in a certain interval of time. So this is how you calculate 1 meter. Interesting fact. 1 meter is calculated as 1 by 299,792,458 of a second. Where did you get this? Where did I get this value? This is nothing but the speed of light. All right. So this is how you can measure length as well. So that is all for today that I have. If you have enjoyed the video, make sure you give a thumbs up, subscribe, and click on those bell notification to get further. Stay tuned. Do visit us at once again www.we-learning.in to get more detail about our classes. So I'll see you all in the next session. In the next session, I will discuss what is accuracy and preciseness of a given instrument. So take care everyone and have a nice day. Bye bye.